Well, hello there again. My name is Bogdan Marin. You might remember me from such videos as the Series Lab and also the Parallel Lab. Now I'm here to bring you one of your favorites, the Balanced 3-Wire Circuits Lab. Well, let's get going. I got 2 cone heaters up there. I've got a transformer here. Okay, not the Michael Bay type of transformers. You're off. This is an actual regular transformer. You got the 110 to neutral, 110 to neutral, or 220 between them. So essentially you're having 2 lines, very similar to what you get in your house. Now, I have lab 2-9 balanced circuits here. What I do is I connect this cone heater and this cone heater each on 120 volts, and I share the neutral in my return. Okay? This is done in circuits. You also will essentially save a wire by doing this. Now you have your 120 here, your 120 here, and your neutral in return. Okay? So what the idea of this is that you have one cycle of your wave, we'll learn about this in AC generation, that is going up, and the other cycle is going down, because you have 2 different waves. So at the peak of both, they're completely opposite to each other. That's why when you take a measurement with your meter and you go phase to phase, you're going to get your 220 here. So when I turn this on, and I use my digital multimeter here, I'm going to set it to volts, and I'm going to go, just to double check my values, line to neutral, I get 118, 118. Now, as you use your voltage throughout the day, the voltage values will vary based on the consumption of electricity. Time at night, obviously, will be higher voltage than the peak time of utilization during the day. Obviously, it dips down. And let's see, line to line here, I should get 220. Oh, I get about 235. Okay, so pretty accurate measurements here. Now, I hook up cone heaters, and a neutral coming back. Now it says, assuming it's a 120, 240 volt supply, calculate the values, the line current. Well, I know my cone heater was 660 watts and I had 120 volts. Well, 660 watts divided by 120, I get about 5.5. When I put my digital my digital clamp on here, I get 5.5. Little Vanna White here, if you guys don't remember that reference, Wheel of Fortune. And on the other side, I get 5.4, 5.5 once again. Now, if I add these 2 lines together, like so, I should get double that, right? Oh wait, I get 0. Why? Well, I think you guys should know, because the magnetic fields will cancel one another out. Or maybe you should know, maybe that's coming up in magnetism after. But the magnetic fields of each wire, as they're going past each other, they're going to actually cancel one another out. So that's why the neutral only needs to be the same size as one of these conductors, because they're both magnetic fields are canceling one another out. Now when I'm putting on the neutral, I get virtually 0. Pretty much exactly 0, I get 0.1. That's because these loads are balanced. Okay, the loads are balanced, meaning that the neutral is going to carry virtually nothing. Virtually nothing. So if I were to even pull this neutral out, this circuit would still work. But I think I just gave away something later in the lab here. Now, calculate the values here. So like I told you, 5.5, 5.5, and 0. Now measure them. Okay, well I just measured them for you guys. Now it tells me to turn the circuit off. These guys are getting nice and toasty. And on the neutral here, put a light bulb in. Does it tell me a 200 watt light bulb? I got a 200 watt light bulb. Now, what do we think is going to happen here? I don't know either. Let's see. Okay, so I got this here. Now, Energize the circuit by turning the main breaker on. Repeat the previous voltage and current measurements. Your source to neutral, line to line, and let's get some voltage values here. So line to neutral, still have 117, 118, line to line, 235, 234. Load voltage here, 117 here, 118. Now this is in series, so this should get something, but doesn't get anything. It's 0.25 ohms, or sorry, 0.25 volts. That's why it's not lit up or anything. Now, does anyone know why this is happening? Why this is happening? Well, you guys actually already know why this is happening here. Because current takes the path of least resistance. This jumper, so current's traveling through here, through this jumper, and back down into here. It doesn't want to go through here and then go back to neutral. It doesn't want that. That common, this jumper here is making sure that this light bulb doesn't see anything, because this path of resistance is substantially smaller than this path of resistance. So the current would rather go through here than go through here. You almost don't even need this one in here. Okay, never do this on a live circuit unless you're a trained journeyman. Okay, so it's the next lab, you're actually pulling this out and turning it on. You're just pretty much removing this, just like so. De-energize it first, then energize it, and light bulb's still not lit at all. So you're going to get the same values as before with this thing not lit. Okay, so again, you're going to have the 5.5 amps, 5.5 amps, 117, 117, 117, 117, and then 234 here. Okay, I've explained a couple of the reasons here, but feel free to look at this on your own and ask me more questions in discussion, or ask me more questions when we go online with this. A really good one, it pretty much just proves to you that a balanced circuit doesn't need a neutral. Okay, now the next one we do is unbalanced neutrals, or unbalanced 3 wires, and we'll show you what happens in that. So make sure you guys tune in for the next video on unbalanced. And that's it for now. Thanks.